Hello, my name is Peter Forsyth. I'm a research engineer from Waterloo, Ontario, Canada. This is a re-recording of a talk that I gave at the Machine Learning and Finance Reading Group. The topic of the talk is transaction costs in deep hedging. My aim in this talk is to show how classical quantitative finance can be fruitfully combined with more recent work on deep hedging. The talk is based on a number of papers I've been reading recently. Here's an outline of the talk. It consists of 4 parts. In the first part, I'm going to give a general review of hedging of derivatives, and more specifically, deep hedging. In the second part, I'm going to talk about some classical quantitative finance insights pertaining to hedging when there are transaction costs. In the third part, I'm going to discuss a paper I read recently by Imaki et al. That attempts to combine the previous 2 topics. That is, it attempts to apply insights from classical results on hedging with transaction costs to improve the design of neural architectures for deep hedging. And finally, I will discuss some conclusions about the paper and some thoughts about future work that could be done in this area. Okay, so let's get started. So the first part is a review of hedging and deep hedging of derivatives. So to discuss hedging of derivatives, it makes sense to start out by defining a derivative. So a derivative is a financial contract whose value depends on some underlying economic quantity. So for the purposes of this talk, we're interested in derivatives trading desks. So the business model of a derivatives trading desk is that they make money by selling derivatives to clients. But in selling derivatives to clients, they incur risk. Why do they incur risk? Well, because the final value of the derivative is based on some economic factors that are not known at the time of the sale of the derivative. They're only revealed in the future. And so therefore, in selling a derivative to a client, the derivative trading desk incurs an uncertain future obligation to that client. In other words, they incur risk. And as an illustration, I've got a plot here showing the payoff distribution of a short put. So you can see that there's a lot of probability density. So the x-axis is payoff, the y-axis is probability density. You can see that there's a lot of probability density concentrated here at 0, but then there's a very long left tail. So from a risk management point of view, this is an undesirable payoff distribution, and it's due to the uncertain future obligation the derivative trading desk has to their client. Okay, so we've said that derivatives trading desks, they make money by selling derivatives, but in so doing, they incur risk. So how can they manage this risk? Well, they manage this risk by hedging. Now, there is an elegant body of mathematical theory that says that if a market satisfies certain assumptions, these assumptions being known as the complete market assumptions, then it's actually possible to find a trading strategy that exactly replicates the payoff of the derivative. And this is true for any future market state, regardless of the outcome. And so in a complete market, actually, a derivative trading desk can completely eliminate this risk we were talking about on the previous slide. Why? Well, because when they sell a derivative to a client, they can immediately engage in this trading strategy, this replicating trading strategy here. And then whatever their future obligation to the client turns out to be, they can meet that obligation, because whatever it is, their trading strategy will have the same value, so they can meet it using funds drawn from the trading strategy. So then in a complete market, it's possible for a derivative trading desk to make profit while completely eliminating risk. That is, they can make a risk-free profit. Unfortunately, for derivative trading desks, real markets are not complete. That is, these assumptions here that are required to come up with a replicating strategy don't hold. And therefore, in general, it's not possible to come up with a trading strategy that exactly replicates a derivative. So then in the real world, the problem faced by a derivative trading desk is to find a trading strategy that approximately replicates the hedging instrument. That is, a trading strategy that minimizes risk, but with the knowledge that it's impossible to completely eliminate risk. There's always going to be some residual risk. The goal is just to control or minimize it. And I've highlighted the word dynamically here to point out that the trading strategy isn't just sort of a portfolio that you come up with once. It's not a static decision to form a portfolio at one point in time. Instead, it's a dynamic trading strategy. It involves repeatedly adjusting your portfolio in response to market circumstances over time. And to emphasize this further, I have this slide here pointing out that hedging is a stochastic control problem. That is, basically the trading desk is deciding on a control policy that is a rule for adjusting their portfolio in the future. And this control policy says that if you observe a certain state, which can be the market state and the portfolio state, then you should make a certain hedging decision. This hedging decision in combination with randomness due to market returns will affect the new state. And then the control policy will say what you should do in response to this new state. So in summary, the trading strategy the derivative trading desk needs to come up with is not a single portfolio, but rather it's a control policy. That is a function that tells you how to adjust your portfolio in response to future market states. Okay, so for any optimization problem, it's necessary to specify an objective function. So here we have the objective function for the trading desk in an incomplete market. So we've written it out here, and let's go through it item by item. So first of all, the trading desk is choosing a hedging strategy theta from the set of all possible admissible hedging strategies, big theta. And their goal is to minimize this quantity here. So first, let's look inside the brackets. We have h theta minus p. So h theta is the final value of the hedging portfolio when you adopt trading strategy theta. And p is the uncertain payoff of the derivative that will need to be made to the client. So remember, we mentioned that in the case of a complete market, it's possible to choose a theta such that h theta always equals p, and therefore all this risk is eliminated. So there's zero residual. Unfortunately, in incomplete markets, that's not possible in general. So h theta is never going to exactly equal p. There's always going to be some residual risk. So the goal of the trading desk is to minimize this h theta minus p, minimize this residual risk. But of course, h theta and p are not numbers, they're distributions. So then we need some way to say that one distribution of residual risk is preferable to another distribution of residual risk. And that's the role of this function rho here. Rho is called a risk measure, and it tells you for each distribution of residual risk, it gives you a number telling you how risky that is. So then, in summary, the goal of the trading desk is to choose a hedging strategy theta to minimize the residual risk h theta minus p as measured by the risk measure rho. Okay, so that's sort of the high-level view of hedging in incomplete markets. Okay, so now on to some more recent work on deep hedging. So a problem encountered when you're formulating and solving these hedging problems in incomplete markets, as described in this slide, is that you sort of have a choice about how realistic do you want your model of the market to be. So if you use a very realistic model of the market, then it may be very hard to solve this optimal control problem here. And so you may not be able to find the optimal hedging strategy. On the other hand, if you choose a less realistic model of the market, you may be able to solve this problem. You may be able to find the optimal hedging strategy. However, the hedging strategy you find may not be useful in the real world because it was derived from a model with many unrealistic assumptions. So there's sort of this trade-off here. And the aim of deep hedging is to sort of bypass this trade-off. The way this is done is that we parameterize this set big theta of admissible hedging strategies, and we parameterize it using neural networks. So we pick some neural architecture, and then every choice of weights for that architecture corresponds to a different hedging strategy. Then the search for the optimal hedging strategy amounts to finding the weights of the neural network which minimize this risk measure. And there are established machine learning frameworks for doing this. Generally, the approach taken to maximize or sort of minimize the risk measure with respect to the neural network weights is either this sort of analytic policy gradients approach that is directly differentiating back from the risk measure to the rates through a differentiable simulator, or a value function-based RL dynamic programming type approach. And there were 2 previous talks in our reading group discussing both of these approaches. So then sort of the pitch, the sales pitch of deep hedging is that, well, using this parameterization, that is using neural networks to represent hedging strategies, we can find optimal hedging policies for more complex, more realistic market models than would be previously possible. And so in some sense, the argument is that deep hedging allows us to mitigate the curse of dimensionality. And there's been a significant number of recent papers on this topic. Okay, so that was my review of, well, hedging in incomplete markets, and also deep hedging, a technique for hedging in incomplete markets. Now let's move on to the second part of the talk. In this part of the talk, I'm going to review some classical quantitative finance results pertaining to hedging with transaction costs. Okay, so it makes sense to start out by defining transaction costs. So when I say transaction costs, I mean costs that are incurred in addition to the economic value of a trade. So what do I mean by economic value? Well, let's say that you decide to buy 100 units of some share. And at the time you make the decision to buy, the mid price of that share is $10. So then I would say that the economic value of the trade is 10 times 100 or 1,000. And then any cost that I need to pay in addition to beyond that $1,000, those would be transaction costs. So here are some examples of transaction costs. So a first example might be fees, that is, payments that I make to some intermediary for the privilege of trade. A second example might be spread. So on any exchange, there's going to be a difference between the best bid and the best ask. Because of this, whenever I buy, I'm going to pay more than the mid price, and whenever I sell, I'm going to receive less than the mid price. This is another form of transaction cost. A third example is market impact. So if I'm a significant player in some market, if I account for a significant quantity of the volume traded in a market, then my trading can move the price. That is, the more I trade, the further I will shift the price against me. And therefore, later units that I trade will receive a more unfavorable price to me than earlier units. This is another form of transaction costs. So those are 3 examples of transaction costs. There are others. And one reason why the study of transaction costs is interesting is because, well, remember that we mentioned previously that real markets are incomplete. And so much of the classical quantitative finance theory pertaining to complete markets doesn't exactly apply. One of the reasons that real markets are incomplete is transaction costs. So transaction costs are a significant reason for the incompleteness of real markets. And although there are other reasons, it's quite important. And so this makes it an interesting and worthy topic for study. Okay, so to illustrate, I thought it would be useful to include a very simple example of a hedging model with transaction costs. So this is probably the most simple example you could think of such a model. Okay, so this model here, it gives an equation for h theta. And remember, according to our earlier definition, h theta is the final value of our portfolio after we've implemented some hedging strategy. So in this simple model, we say that h theta is equal to a sum over n periods. So this is a discrete time model, and in this model, there are n periods. And in each period, we look at the change in the value of our portfolio over that period, and then the sum of all the changes over all periods is the final value of our portfolio. We're assuming that it starts off being worth 0. So in this model, we assume that we have 2 assets, stock and cash. Now, remember we said there that we're summing up changes over every period. So in this period, there are 2 causes of changes in the value of our portfolio. So the first cause is represented by this term here, which is delta I times SI plus 1 minus SI. So delta I is the units of stock we hold in period I. SI plus 1 is the price of the stock in the next period, and SI is the price of the stock this period. So this term accounts for changes in the value of our portfolio due to changes in the market price of the stock between 2 periods. And we're assuming here that the stock price follows some kind of random walk. So that accounts for this term, which is the first cause of changes in the value of our portfolio. We have a second term here, which is the second cause of changes in the value of our portfolio. And this term here, it's C, which is a function of SI, delta I minus 1, and delta I. And C represents, well, the transaction costs we pay when we change our holdings of stock from delta I minus 1 to delta I when the stock price is SI. So this is the transaction cost function. Now, in a more general model, there'd be a third term here accounting for interest we receive on our cash. But for simplicity in this basic model, I'm assuming that the interest rate is 0. Okay, so this is sort of our most basic, most fundamental model of hedging with transaction costs. So there's one thing that I've omitted from this model, and that is, what is this function C? That is, how do we compute how much transaction costs we pay? So there are many sort of types of transaction cost functions that are used in the literature. Here are 3 examples of such functions. So the first example here, which I've called CF, is known as fixed transaction costs. So you notice here that in this model, we pay a fee lambda whenever our holdings of stock differ between 2 subsequent periods. So this is a good model of a circumstance when we need to pay a fee in order to trade, but the magnitude of the fee that we pay does not depend on the size of the trade. In other words, we have fixed transaction costs. The second example transaction cost function here I've written as CP for proportional transaction costs. In this model, we pay a fee that's proportional to the size of our trade. That is, it's proportional to the difference between our holding at time I and time I minus 1. And it's also proportional to S, the current stock price. So this might be a good model of a spread. That is, when there's a gap between the best bid and the best ask, then every unit we trade, we're effectively paying a fee or paying a price equal to half that gap. So this would be a good model of a spread, as I said, and here in this expression we also have an S term. So this model would say that we expect the size of the spread to be roughly proportional to the current stock price. The third example model here I call a CQ for quadratic transaction costs. And as you might expect in this example, the size of the transaction cost we pay is a quadratic function of the size of the trade. And this might be a good model of a form of temporary market impact. That is, if we believe we have an order book with some density Q, then, well, whenever we trade, we're going to move the price against us according to that density. So the more we trade, the more we're going to eat into the order book, and so worsen the price for subsequent trades. And so this idea then is consistent with this idea of a quadratic transaction cost function. And there are many other types of transaction cost functions you could use, but these are sort of the three that we're going to have in mind for the purpose of this talk. Okay, so now let's return to the problem of hedging in an incomplete market, which we previously considered in the previous section. So recall that in hedging an incomplete market, our goal is to choose a hedging strategy theta to minimize H theta minus P. This is the residual risk, where we measure the residual risk using this risk measure rule. Now let's consider what happens when we introduce transaction costs into this problem of hedging in an incomplete market. So one way to analyze this is to use our knowledge that this is a stochastic control problem. So let's consider what are the state variables of our stochastic control problem. Well, first, in the case without transaction costs, note that in this case, it's possible for us to reallocate our portfolio from one set of assets to another set of assets instantaneously and for free when there are no transaction costs. For this reason, when there are no transaction costs, it's not necessary to record our specific allocation of assets as part of our state, because this allocation of assets can be changed for free. In contrast, let's consider the case when we do have transaction costs. In this case, it's no longer possible to change our allocation of assets for free, and therefore this allocation becomes an important state variable. Thus, in hedging problems with transaction costs, we have a higher dimensional state than without transaction costs because we include this portfolio allocation. And this makes the resulting stochastic control problem significantly harder. So this is a problem faced when we're considering hedging with transaction costs, is that basically the hedging problem is harder, it's higher dimensional than previously considered. Okay, so in this next slide, I want to discuss some insights from classical quantitative finance about hedging with transaction costs. So the general methodology in classical quantitative finance is that where we look at the continuous limit of the hedging problem and we apply dynamic programming to this continuous limit. The result of applying dynamic programming is a certain kind of partial differential equation known as a Hamilton-Jacobi-Bellman equation. And this is a PDE for the optimal value function. So if we could solve this PDE, we would know the optimal value function, and from that we could deduce the optimal hedging strategy. So this HJB equation, it completely characterizes the optimal hedging strategy. The problem is this equation can be rather complex. So here's an example of such an equation by this paper by Davis et al. And this is for the case of two assets and proportional transaction costs. So note that this is a four-dimensional nonlinear PDE, which makes it very hard to solve. But even though it's hard to solve, nevertheless, there are some insights we can get by looking at the equation, which we don't need to solve. And we don't need to solve the equation to get these insights. So here I want to emphasize one particular insight, which will be relevant to us later. So let's look at this equation in more detail. I'm not going to go into the meaning of each term, but in looking at it, well, first of all, notice that on the left-hand side of this equation, we have a maximization. And we're maximizing over L and M. So L corresponds to the instantaneous rate of buying the stock, and M corresponds to the instantaneous rate of selling stock. Now let's look at what we're maximizing. So it turns out that we're actually maximizing a linear function of L and M. And because we have a linear function here, we can see that there are actually only a few cases for this optimization problem, and these cases depend on the signs of the coefficients of L and M. So let's enumerate these cases. So the first case is when the coefficient of L is positive and the coefficient of M is negative. In this case, the solution to this maximization problem is to choose L as large as possible and to choose M to be 0. Now remember, when I say the coefficient of M is negative, I mean the coefficient of M including this minus sign. So when this is negative, well, obviously we want to choose M as 0 to achieve this maximum. So then, in this case, the optimal hedging strategy is to buy the stock at the maximum rate. So we could say this is the buy region of the state space. Let's consider the other cases. So what if the coefficient of L is negative and the coefficient of M is positive? In this case, we should choose M as large as possible and L equals 0. So in this case, the optimal hedging strategy is to sell as quickly as possible, and we can call this the sell region of the state space. Finally, if we're in the case where the coefficient of L and the coefficient of M are both negative, then the solution is to choose both L and M equal to 0. So in this case, we should neither buy nor sell. In other words, we should engage in no transactions. And we can say that we're in the no transaction region of the state space. Now, we can do some analysis to show that, in fact, it's not possible for the coefficients of L and M to be simultaneously positive. So we only need to consider these three cases. So this is the insight we can get. Even though it's hard to solve the equation, nevertheless, by this insight, we can realize that the state space is split into three regions. One region where it's optimal to buy rapidly, another region where it's optimal to sell rapidly, and a final region where it's optimal to engage in no transactions. Okay, so let's look at an example of what the application of such a hedging strategy looks like. And this is a great figure from this paper here, which I will reference also in the notes, which I found extremely insightful reading this paper. So I want to take advantage of this figure. Okay, so in this figure, the x-axis is time, the y-axis is holdings of the stock. And this is an illustration of the hedging strategy on one particular path. So see that as we predicted, the state space is partitioned into three regions: a sell region above the orange line, a buy region below the green line, and a no transaction region between the orange and green line. Furthermore, on this plot, we also have the blue line, which is what the optimal hedging strategy would be if there were no transaction costs. The dotted line corresponds to an implementation of the optimal hedging strategy for the case of transaction costs. And we can see that it obeys our analysis from the previous slide. So we started in the no transaction region, so we neither buy nor sell. Eventually, we hit the boundary, enter the buy region, so we rapidly buy stock, returning us to the no transaction region. Afterwards, we engage in no transactions until we again enter the buy region, buy, again enter the buy region, and therefore buy, and then finally engage in no transactions. So this hedging strategy is consistent with our previous analysis. Now you might ask, is this analysis here specific to this case of two assets and proportional transaction costs? And the answer is in fact no. It can be generalized to many other cases. So let's consider one example of such a case. So first of all, let's consider two assets but fixed transaction costs. So remember that fixed transaction costs mean that we pay a fixed fee whenever we buy or sell, but the fee doesn't depend on the size of the transaction. So then in the case of fixed transaction costs, again, we have three regions. So the optimal hedging strategy is similar, but there's one key difference. And that is when we enter the buy region, we don't just buy minimally to return to the no transaction region. Instead, we buy all the way back to the blue line, which remember is the optimal hedging portfolio in the case of no transaction costs. And again, and similarly, when we hit the sell region, we sell all the way back to the blue line. Now, intuitively, this makes sense because in the case of fixed transaction costs, once we buy or sell, that is, once we decide to buy or sell, there's no penalty for the magnitude of our transaction. So we might as well buy or sell to return to the most hedged point, which is this blue line. So I said that this sort of analysis generalizes. So it generalizes even beyond the two asset case. So here's another figure from this paper showing that this analysis generalizes to the two asset case. Beyond the two asset case. So when we have more than one risky asset. So this is a slice of the partition of the input space. On the x-axis, we have our holding of the first stock. On the y-axis, we have our holding of the second stock. And we can see that in this case, we have in the middle here this white region, which corresponds to the no transaction region in this multidimensional case. So if we're in this yellow region, then we trade in asset 2 to return to the no transaction region. If we're in this red region, we trade in asset 1 to return to the no transaction region. And if we're in this orange region, then we trade in both asset 1 and also asset 2 to return to the no transaction region. So this analysis, it generalizes to higher dimensions. Okay, so this sort of analysis is the basis for a large body of work which attempts to use approximate analytical approaches to estimate the various boundaries of these regions. So one famous example is the Whaley-Wilmot hedging strategy, which attempts to estimate the boundaries of the no transaction region in the case of two assets and proportional transaction costs. And the form of this boundary estimate is given here. The estimate is based on some asymptotic analysis in the case of small transaction costs. Okay, so now we're at the third section of the talk. So in the first section, recall that we discussed hedging and deep hedging. In the second section, we discussed classical quantitative finance insights about the form of optimal hedging strategies with transaction costs. And particularly that form involved no transaction regions. In this final section, we discuss this paper, which attempts to apply these classical quantitative finance insights to deep hedging. So here's the paper, here are the authors. So the approach they take in this paper is very simple. It's simple enough that I can summarize it in this one slide. So the authors are interested in a relatively simple case, that is, they want to study hedging with proportional transaction costs and exponential utility in a simple two-asset case. So the neural architecture they use for hedging is as follows. So in this notation, Zi is the vector of information available at period I. And the way that this architecture works is, well, you take in the vector of information available at period I, and you output two numbers, BL and BU, BL being a lower bound and BU being an upper bound. Then remember that delta I plus 1 is your holding of the risky asset, i.e. the stock, in period I plus 1. So the way they compute delta I plus 1 is via this clamp function, which works as follows. So if the current holding, delta I, is less than the lower limit, BL, then delta I plus 1 is equal to BL. If delta I is between BL and BU, then delta I plus 1 is equal to delta I. Finally, if delta I is above the upper limit, BU, then delta I plus 1 is equal to BU. So in summary, as the name suggests, the holding of the stock is being clamped to this interval between BL and BU. So what is the motivation for this neural architecture? Well, the motivation is this analysis we just talked about. That is, this architecture, well, it enforces the partition of the input space that we derived by analyzing this HJB equation. So instead of having their neural network directly output the optimal portfolio holdings, the neural network is instead outputting at every time the location of this green line and this orange line. And then the location of this green line and this orange line, this implies the optimal hedging strategy. So in some sense, this architecture, it's building into its structure something, some aspects of the optimal hedging strategy that we know need to be true based on our analysis of the HJB equation. And so this no transaction band structure, it's automatically enforced and does not need to be learned. And what's the motivation for this? Well, there are many examples from a wide variety of fields where building in knowledge that you have about the right answer into your neural network can significantly improve the performance of the neural network. This is known as inductive bias. And so this is an example of using inductive bias. Okay, and on to some implementation details where they optimize with the analytic policy gradients approach. And they don't exactly use this function. They use a slightly modified version, a slightly tweaked version, where they introduce some slight slopes so that when they're back propagating through this function, they have non-zero gradients. Okay, those are the main implementation details. Now let's discuss, well, what are the baselines they compare against? So they compare against, first of all, the standard deep hedging approach, where you take a feed-forward neural network, apply it to the information available at a time t, and directly output the optimal portfolio holdings in the next period. They also compare it to the Whaley-Wilmot hedging approach, which, if you'll remember, comes from here, which is based on asymptotic analysis, trying to estimate the boundaries of the no transaction region. Okay, so what are their results? Well, first they show some loss curves illustrating their training results. So on the x-axis, we have some measure of training time, On the y-axis, we have a measure of training loss, where lower is better. Here, the black line corresponds to their proposed architecture. The blue line corresponds to this baseline, this sort of standard deep hedging approach. And the orange line corresponds to the Whaley-Wilmot approximation, which of course is not trained, so it's flat. And you can see that the no transaction band network, well, it converges more quickly than the feed-forward architecture, and it converges to a lower value. And furthermore, the level at which it converges is lower than that achieved by the Whaley-Wilmot solution. Okay, and let's look at some test results, which is, so here we have utility, and they're looking at their objective function as a function of the magnitude of the transaction costs. Here, higher is better. And you can see they do well, and they do well particularly in the case where transaction costs are higher. So they're able to learn to adopt their hedging strategy in the case of larger transaction costs. And I guess the two things that are interesting here, well, first of all, they're able to beat the feed-forward neural network, even though it's technically possible for the feed-forward neural network to learn this strategy. That is, there exist weights which would let it learn this strategy. Nevertheless, it's not able to learn it in this example. And also, they're able to beat the Whaley-Wilmot asymptotic solution quite significantly for large transaction costs. And I mean, this makes sense because, of course, we said that the Whaley-Wilmot strategy was derived in the limit of small transaction costs. So therefore, it makes sense that it breaks down for larger transaction costs. Okay, so those are the results for hedging a European option. They also look at hedging a look-back option. And again, the results are similar. They converge to a lower level than the standard deep hedging approach, and they converge faster, and they do better for high transaction costs in their test results. Okay, so finally, let's have some discussion. So, well, what does this tell us? Well, first of all, I think the obvious thing to say is that neural networks are not magic. So just because it's possible for there to exist weights that would let a neural network get the optimal solution doesn't mean that your optimization procedure will actually find those weights. In other words, neural networks are not magic. So anything that you can do to make it easier for the neural network to find the optimal solution tends to be valuable. And so in this case, the authors were able to build in insights about the form of the optimal solution that they learned from analyzing the HJB equation, and building in these insights certainly seemed to be valuable from their results. So they used quant finance knowledge to build a better neural architecture. However, I think that there are quite a few omissions from this paper, which I would like to see in some follow-up work. So, as we said when we introduced deep hedging, one of the main selling points of deep hedging is its applicability to high-dimensional hedging problems. So I would like to see this technique applied to much higher dimensional hedging problems. In this paper, they only applied it to a relatively low dimensional case. And remember, we know that this analysis, it extends to higher dimensional cases. That is, you can still form this kind of partition of the input space in a higher dimensional case. So you would just need to devise a neural architecture that would parameterize this higher dimensional partition of the input space. In my appendix, I've got some even more examples of sort of partitions of the input space for various higher dimensional hedging problems. So I'd like to see this applied there. I'd also like to see more extensive comparison to baselines. So there's, in the literature, in the quantitative finance literature, there's very extensive work. There's a large body of work on hedging with transaction costs. So I'd like to see a more extensive comparison to those baselines. In particular, I find this kind of graph here very useful. So this is a graph from this paper by Zaccagnini that shows sort of standard deviation of replication error and mean of replication error in this sort of Pareto frontier type graph. And every line in this graph corresponds to a different hedging strategy. So it would be very insightful, I think, to include this no transaction ban deep hedging strategy in this kind of Pareto frontier graph. So I'd like to see that. I'd like to also see, well, there are cases when this Hamilton-Jacobi-Bellman equation for the optimal hedging strategy is solvable. So then I would like to see comparisons of the hedging strategy in the case when we can actually find the optimal hedging strategy using this HJB equation. In other words, how does the neural hedging strategy compare to the optimal hedging strategy? Finally, I'd like to see some sort of variation of the hyperparameters that describe the neural architecture. That is, as we add more layers, making our architecture deeper or making it wider by adding neurons or like tweaking some of our optimization hyperparameters, or vary even our training set size, how does this affect the hedging performance, both for the baseline deep hedging strategy and for the no transaction ban strategy? I think this would also be able to provide significant insights. Okay, so thanks for listening to my talk. I thought this was sort of a very interesting paper that managed to combine very classical work with very modern work.